Okay, I think you are all done. Anybody need time more? I normally put 15 minutes, but you can finish it in 5 minutes. It's very easy questions. But you still can, if you're late or whatever, you still could do that. But I can start the lecturing. Um, and if you have a question, you just can start talking or raise hands, whatever you're more comfortable with. Because I need to write in my screen, I just gonna change my video off to don't show my ceiling. Perfect. So let's get started. Happy Thursday. Thursday is a very good day. Yesterday we had a storm here in North Michigan and it was a little hard. Okay. I hope everybody can hear me good. If not, you just can tell me and I can um, make it better or worse. I don't know. So what we had last class and what we're gonna have today. Let's see. Actually, still we are in um, random variables. Let's check if. Okay, so can you hear me good? Again, send me I don't know, thumb or something in the chat. Everybody hear me good? Yes, no? Yes, okay, good. Thank you. I see many students attending in the class. Thank you so much for coming to online class. That's interesting. But you don't have pictures. Please put a picture later to I recognize you guys. I see some students have pictures, but mostly they just have name. Um, but it's good to have pictures, even for Canvas. For attendance part, I need to know who is who. So please put your picture later um, in Canvas too. Okay. So let's see what we talked last class. Poisson random variable. Poisson random variable is actually very important random variable that you can encounter in your career as a electrical or computer engineer. I remember in my comprehensive exam for my PhD, one of my professors asked me about that, and that was very impressive. I wanted to mention how important is this in this random variable. Actually, he asked me, "What is the distribution of what's the distribution of false alarm?" You know, false alarm happening sometimes in radar or any sensors. False alarm is when you detect something that is not real target, that's called false alarm, um, sometimes called outliers. Anyway, he asked me what is the distribution of that. Hopefully I could answer, but here last class we learned that more deeply why false alarm is actually Poisson uh, has Poisson distribution. This was actually one of your questions in your um, quiz as well, something similar like that, I think. So the reason is that the probability is very low, is very rare things that can happen, and but at the same time, the number uh, are a lot, and n is a lot, probability is low, but in multiply p, something constant is given. So that's why most of detection uh, distributions for example, false alarm or detecting noise or something like that in or carrier, like in computer engineering or electrical engineering, considering Poisson. So Poisson is very good uh, distribution to study. Okay, we also learned about um, CDF, cumulative distribution function. Cumulative distribution function is also another way to study random variable. CDF. Uh, let's see if I can. Oh yeah, CDF cumulative. When you add them up, maybe you ask why we add them up. We had probability mass function that give you uh, um, probability of x is equal to x, something like that. Why we want a CDF that is actually capital F of x, that is px is smaller or equal to x. So you can see that why later, but right now we can say, okay, sometimes questions is like that. Instead of asking directly what is the probability of x is equal to something, somebody asked what is the probability of x is less than something. So if they ask us, we can use this accumulative actually distribution function that is coming from sum of a probability mass function. If we call it xi, xi is less than x, something like that. And when we draw that, it's something, because you add them up in each step, is going to be something like a stepwise or a stair shape diagram. So this is a cumulative distribution function, f of the capital X, and this is X. So it's between 0 to 1 because we add them all together, and the maximum is 1 and it stay 1. So less than 0, CDF is 0. More than the bandwidth, um, the bandwidth, for example, is between this and this, between A and B, for example. Bigger than B is 1, less than A is 0, something like that. Okay, so we talk about that as well. So okay, a little more about Poisson to just remind you. Um, we said Poisson is very related to binomial. So because still we want to find probability of x is equal to k, anytime you want to remember what Poisson was, just remember hitting a website. Hitting a website is a very good reminder for you guys. Anytime you want to see if this probability is Poisson, if this distribution is Poisson or not, remember and make it similar to clicking in website. So we want to see what is the probability of clicking in university website in be, for example, 10 times per minute. Okay, so we have time, we have something time, we have we want to find probability of x is equal to something like k, like 10 times clicking, and we know some information, we know some rate, a Poisson rate, that we know, for example, clicking rate per second is, for example, 2. We have something like that. And what is the probability of 10 click per minute, for example, um, we need to find another parameter like alpha, called alpha, that is a lambda t. So when we have alpha, we can write this Poisson um, uh, um, PDF, PMF, probability mass function, is equal to alpha k e minus alpha k factorial. So that was the formula. Uh, and we also explain about this part of that to just remember that's a decay function. Decay function. Decay function is a function that moving from 1 to 0 when um, alpha going to infinity, and this is e of minus alpha. This function called decay function, it's very important function in computer and electrical engineering. You can see that a lot for modeling things. Yes, so I think this was most of the part that we learned. I hope you learned too. You learned this stuff last class. We had some questions in your quiz related to them. I hope you could answer them properly. Okay, what we're gonna do today? So we're gonna move. Still, we are in random variables. Random variables. RV, random variables. We said, okay, you know what is the outcome of this class. The outcome, the purpose, the goal of this class is to model the uncertain universe. We have a world full of uncertainty. We want to model it. How to do that? We need to use some variables. We want to simulate it with math. But before actually um, before defining some axioms for probability didn't consider as a math. So um, in in that time when they defined some axioms for probability, scientists start thinking about make probability as similar to math because we had so many phenomenon that we need to model them. We need to model uncertainty on them. So that's why right now we have a type of math called probability. And without variables, we can't have a math, that's why we need some variables. And so random variables are a function that explain a random outcome. So is assign a number to random outcomes. So in previous weeks, we talked about discrete random variables when this number is a discrete number, countable, 1, 2, 3. But from now to later on, we want to talk about the type of variables that are not discrete anymore. They are continuous. They are not coming from, for example, they are real numbers. So they are real interval. Like for example, x's belong to 0 and 1, for example. So any number between 0 and 1, including 0, excluding 1, for example, I'm saying 1 is not in that interval. Any number in this bit, any real number consider, because real number, when you increase precision, you can make it more and more. You have infinite number between 0 and 1. So it means is a little different than discrete time. So we're going to study these type of variables. Many variables in our job, in computer, in electrical, are continuous random variable. Like for example, the voltage level is always have some tolerance. Like sensors, mostly the output of sensors are continuous. And for example, you are dealing with time. Time is continuous. You can mention like second, like minutes or second or millisecond or nanosecond. Anytime you make it more precise, the probability getting lower and lower. This kind of random variables called continuous random variables. Okay. We also want to move to uh, instead of having probability mass function that give us p of x is equal to x. In continuous form, we can't have this anymore, because in continuous, p of x is equal to x is always 0. Why is 0? Because we always can find something between, so it's infinite number there. So we can, however, we're going to prove that why this is always 0 with some examples. So instead of having this, we need to move, instead of PMF, we need to move to another function, that is a probability density function, PDF, that we're going to talk about that today. Yeah, that's the general thing we're going to cover and you're going to learn today. So, but before jumping to continuous form, let's talk about discrete uniform random variables that we couldn't finish it last time. Because we want to move from discrete form to continuous form, we can use these uniform random variables to do that. Uniform random variables are one of the simplest random variables ever. Anytime you want to remember uniform, just look at rolling a die. Rolling a die is a very simple example of a discrete random variable. So what is discrete random variable? Discrete random variable is a type of random variable that actually probability of all outcomes are same. When you are rolling a die, probability of coming any random space can be uh, 1 s, or this can be 1 2 3 to 6, rolling a die. So when you do rolling a die, this is the sample space. Probability of x is equal to 1 is 1 over 6. Probability of x equal to 6 is also 1 over 6. So they are all equal. So if we draw them, visualize them, if this is x and this is probability mass function, this is okay, I don't need to put that right. Anyway, this is this. So probability for 1 is 1 over 6, 2 is 1 over 6, and 6 is 1 over 6. When we add them together, it's going to be 1. Okay, so this is how we deal with uniform random variables. So okay, so that was for rolling a die. That was very simple. But what about we make it more general, instead of between always 1 to 6, for example, in this case, we can have between A to B or K to L. It was K to L. I changed it to A to B to make it more simpler to explain. Let's clean this up. Okay, right now, imagine you have a random variable that is uniform between A and B. So A and B are integer. Like for example, um, between 2 to 5. Between 2 to 5 means uniform. This means sample space is 2, 3, 4, 5. That's it. That's it. If it's between A and B, means sample space is A plus 1, A, because it's discrete. Remember, it's discrete. 2, B minus 2, B minus 1, B. Okay? Are we all in the same page? Do you get that? What uniform means? Okay, so the uniform means this. If this is uniform between A and B, it means can be A plus 1 to B. Okay? For rolling a die, it was 1 to 6. Okay? That's it. Let's clean this up. So we first of all, we have A and B both integer. A is always less than B, and all integer values between A and B are equally likely. Okay, all integer values between A and B are equally likely. In rolling a die, all values, all 1, 2 to 6, they are equally likely. The probability of happening them is all equal 1 over 6. Okay, if we consider A plus B, first of all, how many number we have between A and B? So imagine between A and B, this is sample space. A plus 1, B minus 1, B. So the number n is A minus B plus 1. Okay, why we wrote like that? For example, between 3 and 5, we have 3, 4, and 5. So 5 minus 3 plus 1 is 3. So it makes sense. So this coming from just counting these numbers, okay? A minus B, we add it by 1. That's it. So let I clean this. So we have the numbers. So if we have the numbers, probability of, because it's uniform, they are all similar probability. Any number, any outcome A plus 1, outcome B minus 1, and B, they are equally likely. Probability of X is equal to X is 1 over N. What is N? A minus B plus 1. That's it. So this is probability. Yeah, we have that here, and X is A to B. And probability of, other than that, I mean, if X is something else, the probability is 0. So we know that too. Key properties. The properties that we have, the number is B minus A plus 1, as we computed here. And mean and covariance. Okay, mean and covariance are a little tricky here. However, we don't need to compute them. I'm not going to ask you to compute expected value, but you need to know some certain things about this. For example, you need to know expected value of X is always equal to sigma between, in this case, between A and B. X is between A and B. X and um, um, and this one. This is a probability mass function, okay? This is probability mass function. But we call that 1 over n, because this is n, okay? So something like that. And if we do, this is a mathematical series or arithmetic series. So arithmetic series is easily, you can find the result. 1 over n can get out, and x is equal from A to B, x. So we need to know two things about arithmetic series. Let I write the formula in case here. First, we need to know uh, sigma from k to 0 to n minus 1. K is equal to n minus 1 over 2, and sigma k square, k from 0 to n minus 1 is equal to actually n minus 1 and 2n minus 1. We can prove them, but it's not in uh, our time to do that. You probably in your math 101 you had that. Anyway, so we consider these two. If we consider these two after some the mathematical the formulation and substitution, you can get this a plus b over 2. Okay, for for um variance also, we're going to have something similar. Variance of x is because the variance, I want you know at least this part. So what is variance? Variance of x is expected value of a square minus expected value of x square. So this is something that I'm going to ask you anytime. You need to remember it. Okay, so because variance is around the mean. Want to see how these random variables varying around the mean. If you remember when we talk about variance, variance is like a distance to the mean, and for the distance we considered a square distance to make it positive, and this square is coming from that. Okay, so you know that. So if we write the same way, uh, this is already given. I mean, let's change the color. So this part is already given. Why? Because we know that. We just need to square this. And for this one, we also can use this formula to find that. Anyway, if you find that also, we're gonna get something like this: b minus a minus 1, that is n. This is n. A square minus 1, 12. Okay, something like that. Yes, so we need to know these things, but you don't need to remember these things. If you want to use them for exams or any other things, you always can bring one paper, a cheat sheet. You can write them up. Um, I'm not gonna ask you to compute this formula, but I might ask you this one. What is variance? What is the relationship between variance and expected value? Or what is formula for expected value? These kind of things that you know. And if you don't know, just go learn. That's easy. Just go learn them. Okay, so this was about uniform random variables, but not continuous one. Again, discrete random variables, discrete uniform. As you can see, why is discrete? Because these outcomes are all discrete: a plus 1, a minus 1, b minus 1, and so forth. Let's do example for rolling a fair die. A fair die is a good example for uniform random variable. So we have in cases for um, actually fair die, n is 6 in this case because it can be 1, 2 to 6. And so is a discrete random variable. Why is discrete? Because the probability of all outcomes are actually equally likely. Equally likely. A probability of coming 6 is equal to probability of coming 1. Okay? So that's why it's uniform. Okay, so do example. One example of uniform in addition to rolling a die, is a robotic case. In robotic um, uh, situation, when you have a mobile robot, a ground robot that moving different directions, imagine it's just moving in four direction: north, east, south, and west. Okay. um, I know it's a little complex. We don't have a type of robot that can move like that easily. Most of the robot can just go angular, like this. They have a steering wheel, but we have some complex, advanced, expensive robots that they can go any direction they want. They can go north, east, south, west. uh, they have different type of wheels that can move in any direction. um, these kind of robots are exist. They have those kind of robot. Imagine this robot is those kind of robot. And possibility of moving in any of these cases are equal. So going to north, uh, the equal um, actually um, uh, probability than going to south or west. They are all equal. We define a random variable. That is, random variable is selected direction. So what cases can be x? X can be one. One is for north, for example. Two for east, and south. Three and four for west. So this is the outcomes. So the outcome is 1 to 4. Okay, so because they are all equally likely, probability of going to north is equal to probability of going to east. So that's why it's a uniform distribution, but discrete uniform between 1 and 4. And probability is all equal. What is n? N is 4 here. So the probability is 1 over n, and is 1 over 4. Okay, so in general, uh, because there is no direction is preferred in this type of robot, and equal probabilities. So and it's finite number of choices. So this is discrete uniform. Okay, that's good. Very simple. So actually, uniform distribution and is simplest distribution ever. It's very simple to explain, to can visualize. Visualization is very important. You need to visualize it. You need to see how this is gonna, because when you visualize it, you can remember it easier. Okay, that was discrete. Now let's move to one more realistic way: continuous random variables. Okay, what is continuous random variables? Continuous random variables are the type of random variable that actually range of random space is from an interval that is real numbers. So this is interval of real number. Like for example, between I don't know, one, between 0 to 1, something like that. But it's real number. This is real number. This is the s of x is belong to this. We have if you remember in math, we have real number, we have integer number, we call it z. We also have n, a natural number. Integer number can be negative, but a natural number is just positive. Okay, it's natural number. So these notations are something that we always use. But when we use r, sometimes we put a line here. I don't know why. maybe for Greek the thing. Anyway, they are showing a real number. When we are dealing with a continuous random variables, we need to have an interval of real numbers. Okay, it's interval of real numbers for sample space. So the idea is that it's a continuous range or an interval of real numbers in that random space. And in that case, a probability of certain point is always zero. Why is zero? Because it's actually there is so many cases when we are increasing the precision, these numbers getting this probability getting smaller and smaller and smaller and smaller, and when the precision go to infinity, the probability going to zero. We're going to prove that soon. So here is some um, intuition or explanation for that. But the main point is we're gonna have infinite possibility value in that interval. So interval of x, because x is still between x is a little less and x is a little high, but this little less or little high, it's showing the precision because this precision can be infinity. Um, so the probability of actually x between these two epsilon, maybe we call them epsilon, yeah, plus epsilon. Um, oh, sorry, epsilon was like that, epsilon and minus epsilon, x minus epsilon, and this epsilon is the smallest number ever. You know, it's coming from precision. So, okay, so this is zero. Probability of that is zero because this portion is very small, very small. Okay, so then let's clean this up. So because there are infinitely possible values in any small interval, so that probability is small. For example, let's think a little intuitively. Imagine I come to the class between 9:25, or class is 9:30, but I come a little early to, fix my computer, stuff, record my things, install the stuff. Anyway, I come earlier a little bit, but sometimes I get late. I come, for example, 9:35, hopefully not leaving the class. And in that case, let's see what is the probability of me come at 9. Okay, probability of x is equal to 9, and x is the time that I'm arriving to. What is this probability? Because this time is not a discrete value, it's not countable. You always can have some precision. For example, you can have precision of 1 minute, precision of 1 second, and a millisecond, and force. So when the precision increase, the probability getting smaller and smaller. So probability get smaller. So let's check it out. If it's, for example, minutes, it can be reasonable. So for minutes it can be reasonable. So probability it's, for example, between these two, between 9:25 to 9:35 we have 10 minutes. So probability of coming like at 9, it can be 1 over 10, for example. This is reasonable. Probability of, in this case. So probability of x is 9, is 1 over 10 if we consider precision as a minute. If we consider it as a second, it's going to be very smaller because this 10 is going to be 10 minus 10 multiplied 60. Okay? This is going to be smaller. If we go to millisecond, again it's smaller. If we go nanosecond, smaller. If we go femtosecond, that is femtosecond is 1 femto is 10 minus 15 second. Almost P of x is equal 9 is 0 because it's 1 over very big number. So it's gonna be actually a very close to 0. So that's why when we increase this precision, it's become 0. Let's do another example to explain why this is in continuous case, this probability of having exact number for probability is not exist. You always need to consider actually interval for that. Okay, let's do another example. Probably you saw these spinning pointers that there is a circle, some numbers, and you are you have a pointer. Imagine there is a pointer and you spin that. So imagine here is 0, and we are doing that counterwise. And imagine this area here, this edge, the length of this edge is 1 meter. This circumference is 1 meter. Okay, so we know that. And we have a pointer here, this pointer that we spin. It can spawn, it is spawned randomly. So when we turn it, it can stop here, it can stop here, it can stop everywhere. But this is kind of equally equal probability. To stop in any of these points, it's uniform. If a stop here is uniform, probability of a stay here is uniform. So anywhere that this pointer stop when you turn it is uniform. In this case, we divided that to 6 arcs. So probability of this pointer stop in portion 1 is equal to portion 3 is equal to portion 5. Okay. So anyway, what is x? X is a random variable that's showing this value that, for example, if x pointer stop here, this is x. X is the distance to the 0, distance of this um, edge between 0 to that point. Okay, let's see. Okay, this is x. And x can be between 0 and 1. Why? Because the maximum is 1 and minimum is 0. Y is equal to 0 because it can be. Y is not equal to why we exclude x, because we exclude 1 because we don't want to count it 2 times. We already, because 1 is in top of 0. So that's why we don't need to consider that 2 times. Okay, let's do some assumption. Every location is equally likely. That's the main point of being uniform. So it's the behavior is uniform behavior. That's cool. That's nice and simple. if we divide the circuits into n equal arcs, like this example, we divide it to 6 equal arcs, okay? Different colors, red, yellow, green, so forth, orange, blue, purple. So what is the probability of uh, um, actually the pointer stay in number n? Because it's 6, n is 6, probability of x is actually n is equal to, is capital X, is equal to 1 over n, in this case 1 over 6, is equal. So this is uniform, and it's actually discrete. Why is discrete? Because we divide it to 6. Okay, that's simple. What about we increase the number of n? Instead of having 6, we make it bigger, bigger, thousand, millions, trillions, and n go to infinity. Are you agree that the size gonna go to 0? Yeah, because the size is gonna go 0 and it's getting smaller and smaller and smaller and smaller. Okay, so and the probability of and probability get smaller and smaller to smaller, because like previous example, when we make precision, the probability have more chance, you know, and when the probability have like an infinite chance, it means probability of x is equal to one of those infinite chance is 1 over number of that infinite chance. So 1 over infinity is 0, okay, mathematically. So that's why this probability is 0 for every x when n is going to infinity. So this is another intuition and explanation of why we can't have in continuous random variables exact probability of x is equal to a number. Okay, I didn't ask any you guys any question about this a spinning pointer on a circle. Is anything that is not clear in this? You can open your microphone and talk if you want. Good. Are you okay? Okay. Okay. Yeah, it's not that difficult. You can understand that. Or maybe I explain it so good. No, I don't think so. Okay, so but that was simple things. Um, okay, so go back to the last class that we talked about cumulative distribution. We talked about cumulative distribution last class, and we said instead of studying random variables with just random variable x and probability mass function that is showing probability of x is equal to x, we can also study another things. Oh, this PMF, we call it P of xx. We also can study random variable with another function. Yes, we can study with another function that called cumulative distribution, that we call it capital F of x, and that was P of x, oh, capital X, of course, capital X less or equal to a smaller x. A smaller x is the values, capital X is the name of the variable, okay? Always remember, the x is the constant value that x can get, you know? Okay, so that was cumulative um, um, distribution function. Why is cumulative? Because it's add up all of actually um, uh, PDF. So this was PDF and this is CDF. So f of x x is um, actually sum of p of x of x, maybe xi, when xi is smaller or equal to x. Okay, this was definition of CDF. Why CDF is important? Okay, CDF is important. Uh, okay, I gotta tell you why it's important, but I am gonna explain it later. It's important because for for all of random variables, CDF is exist. Yeah, CDF exists. Um, so that's why CDF is important. Another point about CDF is CDF is always increasing. It's an increasing function, you know. Um, in discrete form, it was like that. In continuous form, it can be line or curve or like this, but it's always increasing. This increasing probability is very good probability in math. So it means if we get derivative, um, so derivative is always going in a higher direction, and so it means the negative of derivative is going to the lower dimension, a lower point. Okay. So why this is important for optimization is so important, okay? Is important. Anyway, CDF is important because of this amazing characteristic and it always exists. So let's see if we can find any relation of CDF that we studied for discrete random variables with continuous random variables. Or we also have a CDF for continuous. Let's see. Okay, I'm gonna keep this part. Uh, so we know that CDF can work for a discrete random variable, but surprisingly, that can work for continuous as well. It can work for continuous random variable as well. That's very good. So if we can have, why we can have CDF for continuous? Because instead of having this stair shape function, we can have just continuous function without any problem. Because CDF is not dealing with x equal to x is less than x. And you always can add them up. Instead of having sum, you can have integral, remember? So it exists. Yay, it's very good. Okay, so continuous, so we have it for continuous. That's a good point. Very, very good point. Let's see more characteristic of a random variable. We also know that CDF when we go to infinity minus infinity is 0, and when we go to 1, when we go to plus infinity is 1. Why? Because of that axioms that we have for probability. We always need to sum up to 1. Do you remember what was called? What was the name of that axiom? Yeah, any idea? You can open your microphone. What was the name of that axiom that let us this? That when we go to plus infinity, the cumulative, the summation become 1. It was axiom 2. Any idea? You can talk or type. Let's see. 2. Oh, yeah. Normalization. Good. Thank you. Thank you, Jennifer. That was good. So yes, normalization. Normalization means to normalize it between 0 and 1. That's very, very good point. Another things that we also need to consider for CDF that is very important is this. Because I want the space to show that. That's why I show probability of interval between x1 and x2 is CDF of x2, the bigger one, minus CDF of the smallest one. Why this is true? Just with the picture, I can show you why. So this is maximum is 1, minimum is 0, and A and B, for example, is here. Oh, x1 and x2, sorry. X1 and x2 is here. So f of, okay, maybe I make that here, x1 and x2 to make it a little more challenge. Okay. What about f of a CDF of x2? CDF of x2 is going to be this. Oh, sorry, no, I made mistake. This is a CDF is like that. Okay, so do you know what? This levels is probability, like probability of x is equal to 1 is this much. This is probability x is equal to 2 if it's 1, 2. Here is x1, 2 is x1 actually, 2, 3, 4. So this jumping is probability of x is equal to 3 because we add them up, you know, and this one is probability of x is equal to 3, for example. Okay, so so this is probability of x is equal to x2, and this is probability of x is equal to x1. Okay, and when we eliminate these two from each other, we're gonna get this much probability of x1 smaller than x2 is p of x2 minus p of x1. Okay, so oh, sorry, no, this is not, just made me say, this is f of x, this is f, this is f. Okay, so anyway, if we look at this diagram, you can see what this is coming from. Okay, I didn't explain that very clear, but you can get the point anyway. You are smart. Okay, let's see what's happening if instead of having this stair diagram, we have a continuous form. Instead of having that, we have, for example, a line. This is continuous form instead of discrete form. So what's going to happen in this case? So what is the difference between discrete and continuous? In discrete form, we have a step function, and we jump at value of probability mass. As you can see, we jump as a probability mass. This is probability mass function. We jump with probability mass. So the size of jump is p of x is equal to x, as you can see in this example. Good. But what about continuous? In continuous form, you have a smooth function. If it's uniform, this is a line, but sometimes it's not uniform. It can be a curve or this kind of curve, doesn't matter. So we don't have jump anymore, no jump, okay? It's smooth, And a smoothness is always good. You know, you can see that later. Why is a smoothness good? Because it's differentiable. You can get differentiation from it. And differentiation is a basic of optimization. Because with differentiation, you can find what is the minimum and maximum of that curve that is, or objection, what we want to find, you know. Anyway, we're going to see this characteristic later, but let just talk about continuous. So continuous is a smooth, no jump, completely continuous, curve or line, line is also continuous. So in this case, random variable is actually CDF incontinuous. So the random variable, this is another good definition of continuous random variable. Continuous random variable is a kind of random variable that CDF of that is continuous. Wow, that's good explanation, because CDF is always exist. CDF exists all the time. Good. But can we use, let's do example. This example for uniform distribution, let's do that continuous uniform, like that a spinning pointer. A spinning pointer is a continuous form of uniform distribution. So the sample space is a real number between 0 and 1. Let's finish this and wrap it up. What is the CDF? CDF is 0 between 0 and 1 is x, and after 1 is 1. This is CDF, f of x. So this is 1, this is 0, and this is when this is f of x equal to x. So this is the function. That's why we wrote CDF like that. So graphically is a straight line from 0 to 1.1. Okay, a slope is 1. A slope is 1. Okay, can we use probability mass function? No. Why? Because probability mass function here is always 0. No possible. So how we can do this probability? How we can find this probability? We want to see how we can model that. If we don't have PMF, can we have another things? Yes. What about we define something new, call it probability density function, that this probability density function is a derivative of CDF, because CDF is always exists and it's continuous. Awesome. So we can get differentiation. If we get differentiation, we're going to have something else that we call it a small f or lowercase f, and it's called PDF. That is probability density function that we're going to see that next class. Okay, guys, thank you very much for attending in this online class. I hope you learned some little things. And we're going to see you next week inside the class. Hopefully the weather is okay. Okay, any questions? If not, we're going to see you next week. Good day. Have a good day. Oh, somebody wrote something. Okay, normalization. Thank you. Oh, let's see. Thank you. Have a good day. Oof.